So now let's look at Chapter 9, thin film deposition. So what is thin film? So thin film is usually the thickness is less than 1,000 nanometer. So the property of the thin film is different from the bulk materials. For example, in not fully dense, there is stress. It is like a two-dimensional material and influenced strongly by the surface and the interface effect. So typically, there are three steps for the thin film deposition. First is emission of the particle from the source by heat, by high voltage ion bombardment. By heat or by high voltage, this emission of particle source. Then transport of the particle to the substrate, then the condensation of the particles on the substrate. So there are two types of the thin film deposition method. So first one is called chemical vapor deposition. So there is chemical reaction. For example, we have seen this one. The silane decomposed from the silicon about maybe 600 degrees. So there is chemical reaction. So this is the CVD process. So this includes atmosphere pressure chemical vapor deposition, low pressure chemical vapor deposition, plasma enhanced chemical vapor deposition. There is also MOCVD, metal organic chemical vapor deposition. The next one is the physical vapor deposition. Here there is no chemical reaction involved. This includes evaporation, spatial deposition, and other methods. So other methods including semi-coating process, semi-coat, electroplating, thermal oxidation. This one we didn't cover yet. This is the chapter 6. Chapter 6. We have one full chapter to talk about thermal oxidation of silicon. So here are the characteristics of the thin film deposition. First, deposition rate. So usually we want faster deposition rate. The film uniformity across the wafer or from wafer to wafer. Material that can be deposited, including metal, dielectric, or polymer. Quality of the film, physical and chemical properties, electrical properties, breakdown voltage, mechanical properties like stress and adhesion to the substrate, optical properties, transparency and refractive index, composition, film density, defect density, texture, grain size, and impurity level doping. For the deposition directionality, it can be directional or it can be non-directional. For example, when we do evaporation, so we have a source here, like a gold. So we have the wafer here. So heat up, you heat, so the gold atom will be vaporized to form on the wafer. The gold atom will be vaporized to form a film on the wafer. So this is the directional deposition because deposit directional. For the other one, like this is what we'll talk about. So this one is pretty much non-directional. So we have conformal deposition. So you can see here. So this one conformal means non-directional. So the deposition rate along the vertical direction is almost the same as the deposition rate along the horizontal direction. But this one is non-conformal deposition. You can see the vertical deposition rate is faster than the horizontal deposition rate, and the bottom deposition rate is also slower. So this will affect whether it's conformal or non-conformal. This will affect the step coverage of the metal. For example, this one is conformal, good coverage. This one is not conformal. We have poor step coverage. Here again, so this one is the metal deposition on oxide with very good coverage. This one we have a void, so we have void here, poor coverage, oxide on top of the metal. So this one, the filling of the bottom part, this part is not good. The poor filling of the bottom goes via hole, which is a barrier or contact metal. So this is also a problem. So this one is SEM image of the, you can see the void. Usually, the higher the aspect ratio, the more difficult to fill. The more difficult to fill the trench or holes. So there are typically three deposition modes. The first one is called layer by layer growth. This one gives epitaxial film. So in this case, the film atom strongly bound to substrate than to each other. So they prefer to bond to the substrate than bond to each other. This gives the epitaxial film means a single crystal film. So we start with a single crystal atom lattice. This is the lattice. Then we grow a film on top of it. That follows the similar lattice constant. So this gives the single crystal. So this is the best film quality. For example, the deposition of group 3, group 5 semiconductor film like gallium arsenide, so gallium nitride. So those film we use the epitaxial growth single crystal film. So layer by layer. The second one is island growth. Top it forms the island. This is the you can see this in this case the film atoms strongly bound to each other than to substrate. So the film atom they prefer to stick to each other than bond to the substrate. Then we get this island film. The third one is called the mixed growth. In this case, we start with layer by layer. Then we have the island growth. You can see layer by layer. Then we have this island growth. So this is the mixed growth. The second one is island growth. This one is reactive intermixing. So this is not very common. So you can see the mixing. This is not common. So we will talk about epitaxial growth. This is the layer by layer growth. For the polycrystal material, this is usually formed by the island or mixed growth. So this one island or mixed growth. This one give polycrystal film. For example, the deposition of elemental metals usually it is polycrystal. So amorphous film is also called by island or mixed growth. There is no crystalline structure, but there may be some short-range ordering. For example, insulators like silicon oxide, this is amorphous. For the deposition of the metals, if we have the noble metal like gold or silver, so we know noble metal they are inert. So they do not white, no whiting. They try to have the island film growth. So they tend to have island growth. When you have island growth, the film will be very rough. So the film will be very, very rough when you have island growth. To solve this problem, one way we can do is to add adhesion layer of titanium or chrome before deposition of gold or silver. That means if we want to coat silver, so you first coat titanium or chrome, then you deposit the silver. This gives you better adhesion because otherwise the film does not white the substrate. Then the adhesion will be poor and the film will also be very rough. So chrome and titanium give better adhesion because they can chemically bond to oxygen in the oxide underneath. So you have strong bonding. So this is the effect of substrate temperature. In this case, so we have the gold film. So we have 110 nanometer gold film deposited at the 100, 200, 300 degree by evaporation. First, for this case, because this one is the island. This is island growth. Island growth means so they tend to the items tend to form island term by agglomeration. They tend to agglomerate on the surface. So the higher the temperature, the higher the surface mobility. That means the atom come to the surface, they can move around a lot. The higher the temperature, they can move farther away from the absorption site. This way you get bigger and bigger islands because they want to come together. Higher temperature gives them better chance to come together. So this is the low energy state for the case of gold. So you get rougher film, bigger grain. We have higher temperature, so bigger island. So now we look at this chapter. So the first one we look at the CVD. The next one PVD will look in the next slide set. So roughly the chemical vapor deposition, the process. So we have the source gas like saline. Then there is the chemical reaction on the surface to form the film. Then the gaseous product is pumped away. So we input energy including heat or plasma. So this is the typical general CVD process. So this is the systems. system. So roughly speaking, there are 3 types of the system. So those are the 2 of them. So the first one is called atmosphere cold wall system. So the pressure here inside is 1 atm, 1 atmosphere, a cold wall. You can see so here we have the RF induction heating. So we have the radio frequency coil heating. So we have learned that the coil heating heat up conductors. It will heat up only conductors. So this is quartz is glass. This will not heat it up. That's why it's called a cold wall. This cold wall. So this part is cold, but this part is graphite. So graphite is a conductor. So the graphite will be heated. The wafer on top, the silicon wafer on top will also be heated. The second one is the low pressure hot wall system. So here we have the pump. So the pressure is low. So usually the pressure inside is like for example, 1 torr pressure. So this is 1 atmosphere, which is 760 torr. So this is the low pressure. So the hot wall. The hot wall you can see. So we have the resistant heater. We have the resistance. Everything inside will be heated. So this gives you hot wall. So those are the 2 typical systems. The third one is the chamber. So we can also use the chamber. So we have a chamber. We put the wafer here. This is the case for the MOCVD, metal organic chemical vapor deposition. So we will talk about metal organic chemical vapor deposition later on. So this is a chamber. So those are the tube furnace. So this is the this one the tube furnace. A third type is the chamber, like this, a box, a chamber. So we have this is the case for the metal organic CVD process. But this one will be covered in the last chapter, not here. So the advantage of the CVD process, so high growth rate, good reproducibility. Actually it's very reproducible, more reproducible than other methods. Can deposit the material that are hard to evaporate. So what material is hard to evaporate? So you can imagine, so tungsten is hard to evaporate because it's very difficult to vaporize tungsten. Very high boiling and very high melting and boiling temperature. But for the CVD, this can be done easily by using WF6, this gas, plus hydrogen to form tungsten plus HF. You can see, so very easy by the CVD, but hard tungsten. Hard by evaporation. It can grow epitaxial film like this is the like MOCVD, metal organic chemical vapor deposition. This is layer by layer growth, layer by layer epitaxial growth. MOCVD or APCVD. Atmosphere pressure CVD also give you epitaxial film, but this one has to be had a high. So normally when you want the single crystal epitaxial film, you need a high temperature. So the film quality is better than the PVD process, and we have conformal step coverage. You can see the very, very conformal step coverage. So the bottom, the side wall is well covered. So the disadvantage, we need a high temperatures, normally up to some degree. A complex process with toxic and corrosive gases. For example, this gas here can burn in air. If we leave the gas in air, it will burn. The film may not be pure. If we have this gas, you can imagine to form the silicon plus this chemical reaction. Some of the hydrogen will come to the film. This hydrogen incorporation, so the film is not pure. So here are the examples of the CVD reaction. The first one is the thermal decomposition. So for example, to form this one we have seen before, to deposit the nickel by the CVD, we use nickel CO4. So we can also do there are also this kind of process. To deposit tungsten, we can use WF6 plus hydrogen to form tungsten and HF. So this is the reduction, using by the hydrogen. So silicon tetrachloride, hydrogen to form silicon. This is high temperature. This is give you epitaxial film, epi film. So this one low temperature. This one gives you polysilicon film. So this usually higher temperature give you better film quality like epitaxial film, but lower temperature give you polycrystal film. The third one is oxidation. For example, silane oxidized to form the SiO2. Another way to form SiO2 is use this gas, plus N2O. So this is also popular to deposit silicon oxide. And for the deposition of aluminum oxide, we use aluminum trichloride plus CO2 to form the aluminum oxide. Another source of the aluminum is this one. So this is also a popular source for the aluminum. The first one is the compound formation. For example, we use the BF3 to NE3 to form the boron nitride. So trimethyl gallium and arsen to form the gallium arsenide. We can also form the gallium nitride by this gas plus NH3. This is the compound formation. So here to give you some idea of the chemical reaction. So as you can see, the actual chemical reaction can be very, very complicated. So here we have two gases, tetrachloride, silane, and hydrogen. So this corresponds to this one, this reaction here. So it looks like simple, but in reality you can see this is why you have so many chemical reactions. So this one is one way, but all the other reactions, they are reversible. They are reversible. In addition, so we have higher temperature. We do not have film deposition. We have etching. of the silicon. Because you can see, so in this step here, so we can form the hydrochloric acid gas. And this hydrochloric acid gas will etch the silicon to go this way to form the H2Cl2. If you remember, so this chemical reaction is used to prepare electronic grade silicon, as we've seen in chapter 3. So overall, I see there are so many different chemical reactions, and usually the actual process is very complicated. So here are example of some thermal CVD process. So for example, for the single crystal silicon, we need a relatively high temperature to have the epitaxial film. We use those kind of gases. You can see this, but not. We use this gas. This gas usually, this one compared to those one is lower temperature to give you P. So P means polycrystal film. So E means epitaxial. Film. For the germanium, we can use germanium tetrachloride. So gallium arsenide, we will talk about gallium arsenide. So indium phosphide, like this. Silicon carbide, aluminum nitride. Silicon oxide, we talk about silane plus oxygen, and we also talk about SiCl2H2 plus N2O. The silicon nitride, this gas, and from ammonia gas. So typically in the university clean room, so we have this one. This is to give you polycrystal silicon, and we also have this one, but we may not use those gases. We may use other gas like TeOS gas. We also have silicon nitride, and we use this gas for the silicon nitride. So the other material here, they are more coating for the tools. We don't use it too much in the universities. So now let's look at other types of the CVD. So we talk about APCVD, atmosphere pressure CVD. This one is the mass transport limited growth rate. So give you non-uniform film thickness. So we will talk about this later on. The second one is the low pressure chemical vapor separation rate. Low pressure chemical vapor separation. This one, the deposition rate is limited by the surface reaction. So we know that a surface reaction is related to the temperature. That means as long as we maintain uniform temperature, then we got uniform film thickness. This way we can have the film wafer stacked vertically. That means we can have the wafers like this, the wafer stacked vertically, because as long as the temperature is uniform, it gets uniform deposition. So low pressure is normally under 1 torr. So the film quality and step coverage is better. Temperature is usually higher than 500 degrees. So the main advantage for this one is the wafer stack vertically, so we can deposit many wafers at the same time. But for the APCVD, the wafer has to be side by side like this. So we cannot put so many wafers by APCVD. The third one is the plasma enhanced CVD. So in this case, so we have the plasma to help the chemical reaction, to help the chemical reaction. So we can do this at a lower temperature. So when we have the plasma, we do not need thermal energy. We can just use mainly the plasma energy. So we can do at a lower temperature. So the pressure is higher than the spatial deposition. Usually like 100 of milliliter pressure. So usually it is run in the radio frequency 13.56. Usually it runs at this 13.56 megahertz. This will work for the insulators. So when we have the AC, this is AC. So AC it works for the insulators. So the film quality is not as good as the low pressure CVD because the temperature is lower than the LPCVD. So usually, as I said, lower temperature give poorer film. The last one is the metal organic chemical vapor deposition. So why is it called metal organic? For example, we talk about this one. So gallium plus, now this one, ASH3 to form gallium arsenide. So this one is metal, gallium is metal, C3 is organic, so it's called metal organic. So this one we use a chamber. So this one we use auto chamber. This is we use tube. So those two we use tube furnace. So PCVD is chamber, MOCVD is also a chamber. So now we look at atmosphere pressure CVD first. So the process, so we have the reactant transfer through the boundary layer. So we have boundary layer, through the boundary layer, then get absorbed on the surface. Then there is chemical reaction, and then there is the desorption. Then transport through the boundary layer again. Then go to the main gas stream. Now let's look at a simple model for the deposition for the growth rate. So here we have this one. So this is the gas from the gas stream. So here we have the boundary layer here. So the boundary layer here. So this is the boundary layer here. The boundary from the mainstream to the surface. This is the boundary layer. So we have the boundary layer here. So the gas concentration on the mainstream is Cg, and the sample surface is Cs. At sample surface it is Cs. So now we look at the flux. It's called the flux. So the flux is the number of atoms per area per time. So this is the unit of the flux. We look at the flux. So we have the gas molecule from the mainstream, from the bulk into the surface. So we have this flux. This is called F1. Then we have the chemical reaction on the surface. This also consume the gas molecule. This one is F2. So F1 is proportional to the difference between Cg and the Cs. Cg is here and the Cs. So Cg minus Cs type Hg gives the F1. So Hg is the mass transfer coefficient. So F2 is chemical reaction. So it's proportional to the Cs. Proportional to the Cs with Ks. Ks is the surface reaction rate. It's also centimeter per second, like here, centimeter per second, like Hg. In the equilibrium, in the steady state, the flux should be the same. So so flux is the same, F1 equals F2. So you put them together, they are equal to each other. Very simple, this is very easy to solve. You get this formula here. So Cs is given by here. Your Cs is the concentration on the surface. So now let's look at whether this makes sense or not. So if Ks is very big, Ks is much bigger than Hg, then the Cs is approach zero. So you can see if the chemical reaction is very fast, so here is the C. So if the chemical reaction is very fast, then all the gas molecule on the surface is consumed is consumed. It's consumed by the chemical reaction, so the CS equal to 0. On the other hand, for the opposite case, if Ks is much less than Hg, if Ks is much less than Hg, then this will approach Cg. So that means if Ks this will can be ignored, so it approach Cg. So that means if the chemical reaction is very slow, then the concentration, the gas concentration on the surface is nearly the same as the gas concentration far away in the bulk. If the chemical reaction is very low, that means the Cg is the same as Cs. So Cs become here the same level as Cg. If the chemical reaction on the surface is very slow, then the deposition rate is given by flux divided by the N. N is the number of atoms per unit of volume. So flux is given by Ks times Cs. So Ks, this is the flux. Then you get this formula here, Cg over N. So when we have diluent, when the gas is diluted, it becomes the total gas concentration times the mole fraction. So Y is the mole fraction. Mole fraction of the incorporating species. So Ct is the total concentration of all molecules. Y is the fraction of the molecules that is involved in the chemical reaction. So Ct, basically you can consider Ct times Y equal to Cg. Ct times Y equal to Cg. So here we have the rate like this. Then we have two cases. So again, we have those this case and this case. So for the case of the Ks is much less than Hg, then this term can be ignored. So the growth rate is given back here. It's proportional to the Ks. So we know the Ks is dependent on temperature exponentially by the Arrhenius relationship. So we have this. That's the line. So this is the Ks term. So if the Ks is much higher than Hg, so we have the mass transfer limited deposition rate. Then the speed is given by deposition rate given by Hg. So it's limited by the Hg mass transfer term. Hg is a constant. Hg is like this Hg term. Then the overall growth is this the net growth velocity. So here the temperature, lower temperature, higher temperature. So in reality, this Hg term, depends on the temperature a little bit. So this Hg depends on temperature like T power 3 over 2. So we have a little bit in rather than like this. So we have a little bit raise. We have higher temperature. So this is the surface reaction limited. This is the gas transport limited. So you can see this really fit what we observed very nice. Those curves here, experimental data follow this trend. So we can also have the draw gas flow rate and this growth rate. At the low gas flow rate, it is mass transfer limited, so the rate goes up. But when the gas flow rate is high enough, so we come to the surface reaction limited. So this depends on the temperature. If the temperature is the same, then this becomes a flight. And now we look at this curve again. This is the APCVD. But here the partial pressure of the reactant gas, those gases, silane, SiH2Cl2, silicon hydrochloride, those reactant gas, the partial pressure is only 0.8 torr. But Y atmosphere is 760 torr. That means it's only about 1 over 1,000 in those gas. The other 900, the other mostly is the carrier gas. So it's the carrier gas. So the carrier gas is normally it is the hydrogen. So the hydrogen is the carrier gas. So this amount, almost all the gas is actually the carrier gas. For this case, so we have hydrogen as the carrier gas. This is the deposition. So the deposition like this. So you can imagine if we have a lot of hydrogen here, if we have a lot of hydrogen as the carrier gas, this is also a chemical reaction product. This will push the reaction to the left side. When we have too much hydrogen, then the deposition rate is low. So when we use nitrogen, as the carrier gas, then the deposition rate goes up. So this because of this chemical reaction. So this makes sense. So now it is a kind of summary of the growth mechanism. So if the deposition is limited by the chemical reaction, then it is very sensitive to the temperature. And we can have this configuration. So we can put many wafers facing each other like this. So this gives you high throughput. So Hg limited deposition is very sensitive to the geometry. This is the mass transport. So we have to put the wafer like this, and this way the gas transport to the surface is more uniform. So this is the case for the Hg limited deposition. So the silicon epitaxial deposition, normally we need a high temperature. So when we have high temperature, so this term become large, and then it become Hg limited, mass transport limited, Hg controlled. Then we need a horizontal reactor configuration like this, horizontal, to have uniform film across the wafer and between the wafers. So when the film quality is not critical, for example, we can have this amorphous film, then we can have lower temperature. So when we have lower temperature, we can have the reaction. Then this term becomes smaller. We can have the reaction rate controlled regime, and we can do this kind of configuration, because as long as the temperature is well controlled, very well controlled, we get uniform deposition, even though the mass transport is not even. You can imagine the gas to the top is much easier than the gas to the bottom part. But here it doesn't matter because the deposition is controlled by the temperature. This is the main difference between the this one is the APCVD. This one is the low pressure CVD. So we will see this later on. So now let's look at other factors affecting the growth rate. You can see here. So here we have the gas moves from the left to the right. So we have the boundary layers. So this boundary layer is the same as you see here. So this is the boundary layer. So we have this boundary layer. So you can see because of the friction. So the boundary layer, delta S, this boundary layer become thicker and thicker. So we have thicker boundary layer, the diffusion. So we have thicker boundary layer, the diffusion of the reactant gas to the wafer surface will be slower. So that means the deposition rate here will be slower than the deposition rate here, because here we have smaller boundary layer. And also the source gas also deplete along the reactor. So here this make here deposition slower than here, because the gas got depleted along the reactor. To solve this problem, there are 4 ways to do this. First, use tilted susceptor. This support. Susceptor means this part. So we tilt it. This way we get more flow here than the flow here. So we can use temperature gradient. For example, here we use 900 degree. Here we use 925 degree to compensate those effects. We can have the gas injection along the tube. So we can inject the gas along the tube to compensate. We can also use the moving belt. This way everything will be averaged out. And now let's look at the doping. For the silicon wafer, for the silicon wafer growth, we add a dopant into the silicon material. So here is the same thing. So we just add a dopant. We add a dopant into the gas. For example, we can add a phosphine gas, dibarium, arsen, or those are the gas phase at room temperature. We can also add a trichlorophosphine, BCl3, AS. They are all liquid at the room temperature. So we add those gas into the reaction gas. So we add those gases into silane or silicon tetrachloride gas. This way, when you grow the silicon, it will be doped with the phosphine or boron. So the dopant concentration is given by, for the low deposition rate, is proportional to the partial pressure. This is the partial pressure over the dopant species. For the high growth rate, it's proportional to the partial pressure and also inversely proportional to the deposition rate. So you can imagine the faster the growth rate, there is less chance for the dopant to get into the film. But actually, you can imagine, I think this one should always be true. This is not obvious, because I think the faster growth will give you less dopant. But here, you don't need to worry too much about the details of this doping and this mechanism. So now let's look at other type of the CVD, low pressure CVD. So as we see, for the AP CVD has to be done at high temperature. Then we need a horizontal configuration. We put the wafer we put the wafer like this. We cannot put so many of the wafers. So to increase the throughput, we can do LPCVD. That means throughput. I will put a wafer this way, you get higher throughput. So now let's look at here. So for the mass transfer regime, so we care about this term Hg. This one term given by dG over delta S. So dG is the diffusivity. So this one is 1 over proportional to the 1 over pressure. So you can imagine the higher the pressure, the more collision with other gas molecules, then the diffusivity will be smaller. So this makes sense. The delta S is the boundary layer thickness. Is the boundary layer thickness. Obviously, the higher the boundary layer thickness, the smaller transport to the surface. So we have this over delta S term. For example, if the total pressure goes down, then the dG will go up a lot. Hg will also go up. For example, so when the pressure reduced from 1 atmosphere to 1 torr, so reduced by 760 times, so Hg increased by 100 times. This term will increase by 1,000 times. But this term also increase. When you have lower pressure, the boundary thickness will also become bigger. Then increase by 5 to 7 times. It increased by 5 to 7 times. So overall, 1,000 divided by 5 to 7 give you about 100 times. So when we have higher Hg term, that means we can have higher temperature like this here. We can have higher temperature like here can be used, while still Ks is higher than Hg. So even here we have Ks is larger than Hg. That means we are still in the surface reaction controlled regime. So as long as we have even uniform temperature, then we got uniform film, even though we have this vertical stack. So this is the idea of the increasing the Hg. So we can operate at higher temperature, and we still have this. We can still have Ks less than Hg. So here I wrote that. So this is not what I expect. So lower pressure means less reactant. That should have lower rate than the APCVD. This one have higher pressure when for the same temperature. But for the APCVD, atmosphere pressure CVD, the reactant gas is only a small portion of the total gas. As we have seen in the previous slide. So you can see here. So the reactant gas, reactant gas is only 1 over 1,000 of the total gas. So here you can, if you look at here, again you see the same idea. You can see here. So there is the curve. So this curve says this one, with Pg and Cg remaining fixed. Pg and Cg remaining fixed. So the partial pressure of the reactant gas and the Cg is fixed. It's fixed. And that means, so this term, so here, so this Cg term, so this one is fixed. Cg term is fixed. So even though the total pressure may be very, very high. So I read here. So Cg equals to Ct times Y. So we have here CT times Y. So the total pressure, CT, total pressure is very high, but because the partial pressure is very low, so the CG is actually not changed. So when we fix the CG, then the rate is only limited by the HG term. It does not depend on the CT. That's why it writes clearly. That's why it written clearly. The CG has to be fixed. Then you have this condition. Otherwise, if the CG goes higher, otherwise the APCVD should give you higher deposition rate. If the CG, we use pure gas, no carrier. So if you use pure gas and no carrier gas, then APCVD will give you higher deposition because the CG term will be very, very high. So usually, this is a tube. So this is the tube. This is a glass tube. The actual course. Sorry. So the tube here, inside here, it is cross glass. So normally the pressure is 0.25 to 22. Temperature is over 500 degrees. So here we have because we have the chemical reaction limited rate. So we can put the wafer stack vertically. So we can have 100 to a few hundred wafers per run. This gives you very high. Throughput. So as long as the temperature is uniform, so we need a very, very good control of the temperature to be within plus minus 1 degree. We need a very good temperature control. That's why you see it here. So for the LP CVD, for the low pressure CVD, so we need this one. This is the hot wall system. So we have the resistant heating that gives you very good temperature control. So this one temperature control is not very well, but the mass flow control is better. And because we run at the low pressure, we do not require no carrier gas. Because low gas pressure, we can reduce the gas phase reaction. That means if we have a wafer here, there is only deposition on the wafer, no deposition in the gas phase. Otherwise, if we have the gas phase deposition, there will be a lot of particles. That will form on the wafer to contaminate the wafer. So we have the higher pressure, high CG. For example, we have high CG. If the partial pressure for the silane is very high, then there may be a gas phase reaction. That is bad. But for the low pressure, this is the CG is not very high. Then we do not need a carrier gas. We do not need this carrier gas. Is also actually called diluent. So the purpose for the carrier gas is to dilute the main gas to avoid a gas phase reaction. So now we look at a plasma enhanced chemical vapor deposition. So in this case, so we have the RF plasma. Radio frequency is 13.56 megahertz. So when we have the plasma, so the plasma provides a lot of energy. It forms the radicals. That is very reactive. This way, we can do the deposition at a low temperature. So basically, so the plasma gives the energy, then deposition can happen at the low temperature, so even at the room temperature. For instance, so when we found this one, so we need 600 degrees to decompose. But when we have the plasma, it will form something like this: HIH2, HIH3, HIH3, or HIH. So those are called free radicals. So those free radicals, they are very reactive. Very reactive. So this will help to form the film. Then we have for the deposition of the silicon oxide. So when we have the plasma, the oxygen will become O plus O. So those atomic oxygen is much more reactive than this oxygen molecule. So this is the role of the plasma. So we can do the deposition at a low temperature. because we no longer need the thermal energy for the chemical reaction. When we have low temperature, this is good for the metal deposition on like aluminum. So we know aluminum will be melted. About 650 degrees, aluminum will be melted. We can also do this on the polymer. And then we can make, for example, plastic solar cell. So we have professors at the ECE who work on a plastic solar cell. So what they do the amorphous silicon by PCVD on top of the plastic sheet to make the plastic solar cell. Because PCVD can do low temperature, so plastic will not be burned. So substrate temperature has some effect, and this will affect the film quality. So normally, higher temperature gives you higher film quality. So when we have the plasma, we have the ion bombardment. As a result, those ion bombardment will help to make the film more uniform and more conformal coating. Because the ion bombardment improves the surface diffusion. This way we can have more uniform film coverage, more uniform step coverage. This is conformal. More conformal step coverage. But this is not as conformal as the LPCVD process. Disadvantage, plasma damage, not very pure film, because we have a lot of hydrogen come from those hydrogen here come to the film. So here are the conditions for the typical PCVD process. So temperature is sometimes go to 400 degrees, so 100 to 400 degrees. For the casing of the CNT, carbon nanotube, so people can do PCVD carbon nanotube at high temperature. So the flow is 10 to 100 of SCCM, standard cubic centimeter per minute. So higher flow rate can increase the deposition rate and the uniformity. The pressure is 50 milliliter to 5 torr. This changes the energy of ions. The ion bombard the surface. So the ions will bombard the surface. So the atom will move around. The atom can move around by the ion bombardment. This gives you better film quality, so denser film and the more uniform film. So the higher pressure, lower energy ion bombardment. Change the deposition rate, and if we have too high pressure, we have the chemical reaction in the gas phase. This is very bad. If we have the reaction in the gas, then there will be particles. So the particles in the gas formed in the gas will fall on the wafer. So power, so 10 to 100 watt. So higher power gives you higher deposition rate, but too high power may have the chemical reaction in the gas from the particles falling on the wafer surface. So frequency is almost always 13.56 megahertz. So this is kind of a industry standard. So here are the examples of the PCVD system. For the amorphous silicon, we can use the silane at this temperature. We can have even lower temperature. Epitaxial silicon, higher temperature can do the epitaxial silicon. The silicon nitride, we use this gas, but normally we use just silane and this gas. Nitrogen will also work. Silicon oxide, we can use silane and N2O. So tungsten, so other materials, they are more for the coating. To make very, very hard for the cutting tools, abrasion cutting tools. They are used for the industry, but not used much in the lab. But in the lab, in the university, so normally we have this one, and this one. Those are the three popular films for research lab. So those are the source gases for different film and at different temperatures. So lastly, we talk a little bit about it's called selective deposition. So in this case, there is deposition here, but no deposition on the other surface. So in the end, we form a film only in a trench. So this, for example, the deposition of copper from this precursor gas, this complicated organic precursor gas. This will happen on the metal, but not happen on the silicon oxide. Another example is that, so the silicon When we grow the tungsten or moly, they grow faster on the silicon than on the silicon oxide or silicon nitride. So this one is the laser CVD. So in this case, so we talk about a thermal CVD and also plasma. So for the thermal CVD, the heat provides energy. Plasma CVD, so the plasma provides energy. For the laser CVD, so the laser provides energy. So we can laser provide energy. So we can move around. We move the laser, the laser beams. We move the focal point, the laser. So we can move the laser focal point. We can move the laser focal point around to get something like this. Okay, thank you.